Okay. So I'm sure you remember when we solve an equation, let's say a radical equation, x plus 1 equals 2 minus 3x. What do? We square both sides. Another type of equation like x squared equals 4, we take the square root from both sides. Similarly, we can differentiate both sides. Now, I have to be very careful because this is an inner function, this is the outer function. This is the inner function, this is the outer function. This is a product of two different functions. It's a mess. Okay, not quite. So let's differentiate y cubed. Remember, y cubed is a function raised to the third power. So when I differentiate y cubed, I get 3 times y squared. Y is a function, so times the inner function prime. I will not write y prime. I will write dy over dx. This is only this piece. Plus, I don't like messing with constants. If it's a factor outside, it can wait. I differentiate x squared, multiply by the second function, plus the first function multiplied by the second one prime. I'm not going to write y prime. I'm going to write dy over dx. Equals. Now, I'm getting in trouble because I haven't gotten the chance to present natural log. So I have to change that because natural log is in the next section in 3.6. My apologies. I had, for a moment, I forgot about that. So I'm going to change this function into just delete the natural log. Sorry, I can't show the natural log just yet. I will give it the formula because it's right here, but I would like to talk about it when time comes. So natural log of y will be 1 over y times y prime. So we're going to talk about it later. So for now, I'm just going to remove the natural log. It's in the next section coming up, hopefully tonight. I got carried away. Okay, so then the answer is the derivative of that function, dy over dx. So now the question is, what happens next? Well, first of all, I have to distribute the 2. Rearrange a little bit if I need to. And then we'll talk about the next step. So then I have 3y squared dy over dx plus 4xy plus 2x squared dy over dx equals dy over dx. Now I'm sure everyone understands that this is our variable. This is what we are after. This is what we want to determine. So at this point, this is a linear equation in dy over dx. These two terms will go to the other side because they have the variable. This term will stay where it is because it doesn't have the variable. You can say, why don't you do the other way around? Why don't you move this here and then this here? That's fine too. But for now, I'm just going to take these two terms because they have the variable next to the other one that has the variable. So I have 4xy equals, and at the same time, I will factor out dy over dx. I have a positive 1, I have a negative 3y squared, and I have a negative 2x squared. When I move a term from one side to the other, all I do is change its sign. So the 4xy stays. These three terms are all on the right-hand side of the equation of the equal symbol. And I factor out dy over dx. This is the positive, this will go to negative, and this will become negative as well. At this point, I'm ready to find an expression. Yes, you can say, yeah, what did you accomplish? Not much. Your expression still has y in it and you don't have it. True. But it's a great accomplishment because we will be able to determine values. we will be able to determine values. If we are given x and y, we will be able to determine dy over dx, which makes a huge impact, or it's a huge result for us. So obviously, since I'm solving for dy over dx, it must be 4xy divided by all this. 1 minus 3y squared minus 2x squared. So this is an expression for a function that I don't even have. So it's an expression of its derivative. If I have a point for this, let's say point A comma B, and you say this point is on the equation, find me the rate of change of the function I don't have at the point A comma B, no problem. I'm going to evaluate when x is A and when y is B. I will plug them in and I will get whatever number. So I can determine the value of that derivative. I just cannot give you the derivative in terms of x only because I don't have y. So feel free to choose.
Why can't we use y prime there? Why do we have to use dy over dx?
Because the notation will be confusing and you may miss the y prime by mistake and you will not correctly identify the answer. Please don't use y prime in implicit differentiation. Please. If you write y prime and you don't see the prime and you keep this on this side, the whole thing is a mess. That's why I highly recommend this notation for implicit differentiation. Okay, any questions? Would you like to choose anything? Or these problems are in 3.5. Okay, I will choose. Thank you. E to the y times sine x equals x plus xy. If I'm asked to find dy over dx, not only that I will not, most probably not mess up the notation, but this clearly states, the notation dy over dx clearly states that y is a function of x. So like before, we will differentiate both sides. Who would like to get it started, please? If no one volunteers, then I will ask.
So for the left side, there would be e to the y cosine x.
E to the y times
dy over dx.
Very good.
Okay.
Multiplied by the first function plus, I continue here, plus e to the y times cosine x, very good, equals. This is alone. This was a product. We had to use the product rule. This is alone, and this is the variable. So this is just one. Say it again. I'm sorry. Forgive me.
I have a question.
Yes.
So next to the plus e plus y times cosine x, but we have to do dy over dx in front of the cosine x because it's the differential.
Okay. The product rule says the first function prime times the second function plus the first function times the second function prime.
So is the reason we don't write dy over dx because we can't essentially make the prime of e over or y over e, or e to the power of y?
Okay, so let's talk about this again. So leave some room. I'm going to come back. First function times the second function prime is the first function prime times the second plus the first times the second function prime. Is this okay?
Yeah.
Perfect.
Yes.
Perfect. So now, this is this. This is this.
So what's the purpose of writing dy dx?
Because it's e to a function. E to a function prime is e to the function times the function prime. E to the function times the function prime.
Oh, so we don't have to do cosine because it doesn't have y in it. So
Exactly.
Okay, I get it.
So now 1 is e to the y, 2 prime, sine prime is cosine x. Is that okay? Is that a yes? Is that a no?
Yes, thank you.
Thank you. Everyone on board? Okay, so now x is the variable. It's just x, so it's x prime is 1. But now here I have to use the product rule again. So plus, the first function prime is 1 times the second function plus the first function times the second function prime. What do I write for the second function prime?
dy dx.
Excellent. Okay, so this is what I got. I will write it again because it's squeezed here in a corner because I wrote all sorts of stuff around it. So I'm writing it again. So you don't have to. dy over dx times sine x plus e to y cosine x equals 1 plus y plus x dy over dx. And as we know, this is what we are after. I'm going to move this term next to this one, and I'm going to move this term to the other side. When I move this term, because I'm lazy and I don't want to write all this again, I will already factor out e to the y sine x minus x, everything times dy over dx. So this becomes negative when I move it. The ey sine e to y sine x minus x, they both have the same factor, which is the variable in the problem. And then on the right hand side I have 1 plus y minus e to y cosine x. And now can anyone give us the final form of dy over dx? I'm losing my voice, hold on 1 second.
We do 1 plus y minus e to the y cosine x over e to the y sine x minus x.
Brilliant. Thank you, Mickey. 1 plus y minus e to y cosine x, e to y sine x minus x. This is it. Again, if you say, what is all this? What have you accomplished? You determine the derivative of an expression that has y in it. True. It's very valuable, though. Do we need more examples? Do we need more examples with implicit differentiation?
I'd like one.
Please.
One more.
Okay, would you feel comfortable choosing in 3.5, or you want me to choose?
Would you choose one, please?
Yes. Let's say tangent x minus y equals y divided by 1 plus x squared. Is this okay?
Yes.
Perfect. So again, the question here is asking us to find an expression for dy over dx. For whatever reason, we need that to find the rate of change of the function that we don't have at different points.
Professor,
Yes, anything. Oscar?
will we be told to do this implicit differentiation, or are we supposed to look at that and be able to recognize that that is an implicit differentiation?
Very good question. So I may not say implicit differentiation, but I may ask you to find dy over dx. You have no choice. You will not be able to solve this. No one can solve this in a million years by hand. So if you're asked to find dy over dx, it's very clear y is the function of x, and we have to use implicit differentiation, but it's a very good question. So we differentiate. I'm ready. Who would like to start? Tangent prime?
Secant squared x.
Very good. Secant squared of x minus y times the inner function prime.
One minus dy over dx.
Brilliant. Does everyone understand this?
Yes.
Thank you. The right-hand side is a mess. We will start with the denominator. What do I have to do to the denominator?
Square it.
Very good. Awesome. Great job. Now, we use the quotient rule. The top function prime, what do I write?
dy dx.
Perfect. Thank you. Times the denominator minus. Watch me. Run out of room again and again. That's my habit. What can I say? Copy the top, and oh, I think I'm going to be okay. Times the denominator prime.
2x.
Ah, look at that. Now, this is messy. Here is why. First of all, this is an expression that needs to be distributed to these two terms, to 1 and to blah, blah. So, secant squared x minus y minus secant squared x minus y times dy over dx. I'm going to write below because I know I'm not going to have room. Now, notice what happens here. Here we have two terms divided by 1. I can separate them. The pink over the denominator and the green, yellow over the denominator with minus in between. This over this minus this over this. So that's what I'm going to do. So this is these two, 1 plus x squared over 1 plus x squared squared times dy over dx minus 2xy over 1 plus x squared squared. Now look carefully and tell me what's happening here. I can get rid of something. Of what? So at the same time, I'm going to move this term to the other side and move this term to this side because I don't want to write all this 3 times. That's how lazy people do it. So secant squared x minus y, but plus 2xy over 1 plus x squared squared equals, this is positive, it's 1 over 1 plus x squared. This one becomes positive, secant squared x minus y, and I've already factored out dy over dx. Of course, I had to run out of room. Otherwise, I would not be myself. Okay, so finally, since this is our variable, we divide this by this. This is the number or the quantity. A second, don't forget the second parenthesis, the paired with this one. So we have x minus y here, but also a big parenthesis with a factor outside. So then this dy over dx will be, all this is in the denominator, 1 over 1 plus x squared plus secant squared over x minus y. And this is, whole thing is in numerator. Secant squared of x minus y plus 2xy over 1 plus x squared squared. Yes, you can find the least common denominator, simplify a little bit. I'm happy with the way it is.
So I have a question for you.
Yes, please.
Will we ever be asked to find, like, solve for x instead of y? Like, pretty much reverse, but for x, so it'll be like...
I could be asked. Yes, it's a very good question. So if I'm given, let's say, x or y squared plus 2y equals x to the third, if I'm asked to find dx over dy, this means that x is a function of y. So now x is the function, so when I differentiate x, I get dx over dy times y squared plus x times the variable prime 2y plus the variable prime, which is 2, equals x cubed, which is prime, which is 3, x squared dx over dy. I can be asked any combo. So then I'm going to bring this here. So these two are 2xy plus 2 equals 3x squared, but minus y squared. And I immediately factor, sorry, habit. And it's dx over dy. And all I need to do is just divide. So then dx over dy will be 2xy plus 2 over 3x squared minus y squared. And I have to let it dry, and I'll have to put an x in there. It worked.
Thank you. Literally, I don't understand how you go without making that many errors in Sharpie. Like, I would have to use whiteout all over.
Well, that's all I know. You have other talents. I don't. So, any questions on this?
I have a question on the question we just did.
Yes? This one or the previous one?
Yeah, this one.
Okay, ready?
Yeah, so can you go up a bit?
You mean this way?
Yes.
Okay.
So the 1 minus dy dx, where'd you get that from?
The inner function prime. X prime is 1 and y prime is dy over dx. So if this is tangent x, you just have secant squared x, but it's tangent of a function. So when we differentiate tangent of a function, we get secant squared of that function times the inner function prime.
Oh, okay. Okay, thank you.
Better?
And so on the right side of the function, the reason why we just have a singular y is because it's just the function, not the function prime.
Is that okay, Tan?
Well, no, I'm asking.
I couldn't hear you. I'm sorry, I couldn't hear.
Oh, no, you're good. I said this that way on the right side. We just have the singular y there because of the, whatchamacallit?
The quotient rule.
Yeah, the quotient rule.
Yes.
Okay.
So the function at the top prime times the denominator minus the function times the denominator prime. And here I had no choice. I had to remove the dy over dx somewhere, so somehow from there, so I had to separate.
Okay, I got you.